Right now, in the room around you, in the air inside your lungs, in the emptiest gap between the stars, empty space is boiling. Particles flicker into existence and vanish before anything can catch them. And when scientists added up the energy hidden inside all of that nothing, they got a number so enormous it should have torn the universe apart the moment it was born. Tonight, we go inside the quantum vacuum, a hidden ocean of energy, the worst prediction in the history of science, and a bubble moving at the speed of light that could quietly erase everything. Before we go any further, if questions like this are the kind of thing you love sitting with, a quick like or subscribe really helps the channel grow. Now, let's begin. Take everything out of a sealed box, pump out the air, remove every speck of dust, every stray atom, every drifting particle of light, then cool the walls down toward absolute zero, minus 460 degrees Fahrenheit, the coldest temperature nature allows. What you are left with is a perfect vacuum, the purest nothing a human being can build. And it is still completely full. This is the first strange truth about empty space, and it quietly undoes something you have believed your entire life. You picture a vacuum as a still, dark, silent void. Physicists looked as closely as anyone ever has, and they found the opposite of stillness. The vacuum churns, it shivers. At the smallest scales imaginable, empty space behaves like the surface of a pot of water held forever at a rolling boil. To understand why, you have to shrink your imagination down past the atom, past the tiny parts inside the atom, all the way to the level where reality is built out of fields. A field is something spread across all of space, carrying a value at every single point. The air in your room has a temperature at every point in it. In the same way, the universe has invisible fields laid over every scrap of space, including the empty parts. And these fields are never perfectly calm. Here is the picture that helps. Imagine an ocean seen from very far above. From orbit, it looks flat and smooth, a motionless sheet of glass. Fly closer, and the illusion falls apart. The surface is alive with ripples, swells, and foam that never stop moving. The quantum vacuum is that ocean. From a distance, empty space looks like nothing at all. Up close, at the tiniest scales, it heaves with restless energy that can never be switched off. And this is where the real trouble begins. If the vacuum carries energy, then the emptiest cubic inch of space is holding something. This is a real, physical quantity the universe is forced to account for. Every gap between the stars, every hollow space inside every atom in your body is filled quietly with this hidden energy. For most of the history of science, nobody lost any sleep over it. The energy seemed far too small to matter, a rounding error in the great accounts of the cosmos. Then physicists sat down and tried to calculate exactly how much of it there was. They expected a modest, sensible number. What the mathematics handed back instead was a figure so violent, so far beyond anything reasonable, that it would earn the name of the worst mistake any theory has ever made. Before we reach that number, though, we have to understand why the vacuum refuses to sit still in the first place. Why can empty space not simply be empty? Why can the fields not relax down to zero and stay there, calm and quiet forever? The answer hides inside one of the deepest rules in all of physics. It is a rule that forbids anything in the universe from ever being perfectly at rest. It applies to atoms, to light, and to the vacuum itself. And it means that total stillness, the pure nothing you imagined inside that sealed box, is a state the universe simply will not allow. To understand the boiling vacuum, we first have to meet the law that makes stillness impossible. There is a law in physics that sounds impossible the first time you hear it. Nothing in the universe can ever hold perfectly still. Not an atom, not a particle, not the empty space we just described. Everything, at the smallest scale, is forced to keep moving forever, and it has no say in the matter. The law is called the uncertainty principle, and it is one of the most tested ideas in all of science. In plain language, it says that nature refuses to let you pin down two things at the same time. You cannot know exactly where a particle is and exactly how it is moving, both at once, with perfect precision. The more sharply you fix one, the more the other blurs and slips away. Now follow what that means for stillness. To be perfectly at rest, a particle would need to sit at one exact spot, not moving at all. Its position would be pinned down perfectly. Its motion would be pinned down perfectly, at exactly zero. Both quantities nailed to a single value at once. And that is the precise thing the uncertainty principle forbids. A particle frozen in place would break the deepest rule in the rulebook. So nature strikes a compromise, even at the lowest possible energy, even when every last scrap of heat has been drained away. A particle keeps a faint, permanent quiver. It never stops trembling. Physicists call this leftover motion the zero-point energy, the energy that remains when there is no energy left to remove. Picture a child on a swing. In the ordinary world, the swing slowly loses height, drops to the bottom, and hangs there, still. In the quantum world, the swing can never fully stop. Even at its lowest, calmest point, it keeps a tiny, endless jitter back and forth forever, because coming to a complete halt is simply not allowed. Here is the part that reaches into everything. Those invisible fields we met in the last chapter, the ones spread across all of space, behave exactly like a vast collection of these restless swings. At every single point in the vacuum, in every direction, the fields carry that same unavoidable quiver, and each quiver holds a little bit of energy. One quiver is nothing. But space is not made of one point. It is made of a limitless number of them, packed together with no gaps at all. Add up the tiny leftover energy at every point, in every field, across every possible way a field can wobble, and the small becomes staggering. The gentle, harmless trembling of the vacuum begins to pile into a total that grows and grows the closer you look. This is the seed of the whole crisis. The vacuum boils for a stranger reason than heat. It boils because the laws of quantum mechanics will not permit it to be still. The energy is baked into the structure of reality itself. You cannot cool it away. You cannot shield against it. It is simply there, in every corner of the universe, the price the cosmos pays for forbidding perfect rest. And that raises an uncomfortable question. If empty space is quivering with energy at every point, where do all those particles come from? Because the vacuum does more than tremble. Every instant, in every direction, it reaches into that trembling energy and pulls real particles into being, out of what looks like absolutely nothing. Watch a small enough patch of empty space for a short enough moment, and you will see it break its own rules. Out of nowhere, a pair of particles appears. A particle and its mirror opposite, its antiparticle, born together from empty space. They exist for the briefest flicker of time. Then they rush back together, cancel out, and vanish, leaving the vacuum looking exactly as calm as it did before. This happens everywhere, constantly, in every cubic inch of the universe. Right now, trillions upon trillions of these ghostly pairs are flashing in and out of existence in the space around you. It sounds like a magic trick. Making something from nothing should be the one thing the universe never permits. Energy is supposed to be conserved. You cannot spend what you do not have. So, how does empty space keep paying to create particles it never seems to run out of? The answer is a loophole, and it comes straight from the uncertainty principle we just met. That rule has a second face. Along with position and motion, it also ties together energy and time. And it says something remarkable. For a very short moment, the amount of energy in a patch of space is allowed to be uncertain. The universe lets you borrow energy from the vacuum, as long as you pay it back fast enough. The rule is strict about the terms. Borrow a little energy, and you can hold it for a fairly long time. Borrow a lot, and you must return it almost instantly. It works like the harshest loan shark imaginable. The bigger the loan, the sooner the debt comes due, and the deadline is never open to argument. So the vacuum borrows. It pulls just enough energy out of that endless quiver to create a particle, and its antiparticle holds them for a heartbeat, then slams them back together to repay the debt before the universe can notice anything is missing. The books always balance. The loan is always repaid. Nothing is ever truly made for free. Physicists call these fleeting creations virtual particles, and here is why they matter. They are only ever temporary. Born from borrowed energy, they live for an almost unimaginably short slice of time, then annihilate back into the field while fresh pairs are already appearing to take their place. The vacuum is a churning crowd that never stops swapping its members. To picture it, imagine the surface of a fizzing glass of soda. Bubbles appear from nowhere, rise, and pop over and over, faster than the eye can follow. The liquid looks still if you only glance at it. Look closely, and it is seething. The vacuum fizzes like that, except the bubbles are particles, and the fizzing never runs down, never goes flat, never stops. And these ghost particles are more than a curiosity. They leave real marks on the world. They nudge the paths of light. They tug on the particles inside atoms. They are constantly reaching out of the borrowed dark and touching the solid, ordinary matter you are made of, which means we should be able to catch them in the act. If the vacuum is truly fizzing with hidden particles, then somewhere, in some experiment delicate enough, their invisible pressure should push on something real, something we can actually measure. And in the year 1948, one physicist worked out exactly how to feel it. In 1948, a Dutch physicist named Hendrik Casimir asked a simple question. If empty space is truly full of these flickering particles, could you ever push on them? Could you feel the pressure of the vacuum itself? His idea was elegant. Take two flat metal plates, bring them extremely close together, almost touching, with nothing between them. No air, no light, only vacuum. Then watch what happens. Here is the trick. Those virtual particles flickering through space come in every possible size, every possible wavelength, like waves on the sea rolling in at every length from tiny ripples to long, slow swells. Outside the plates, there is room for waves of every size to exist, but in the narrow gap between the plates, only certain waves fit. The gap is too tight for the long ones. It quietly excludes them. So the space outside the plates stays crowded with vacuum energy of every wavelength, while the space between them holds less, more pushing in from outside, less pushing back from within. The vacuum on the outside wins, and it presses the two plates together, two solid metal plates, drifting toward each other, shoved by the pressure of empty space. Consider how strange that is. You put two plates in a perfect void, touching nothing, connected to nothing, and they move. Something with no air, no magnets, no visible cause reaches out and pushes them. The only thing between them is nothing, and the nothing is doing the pushing. For decades, this stayed a prediction on paper, too delicate to test. The force is absurdly weak at any distance you can see. It only grows strong when the plates come within a whisker of each other, closer than 1,000th the width of a human hair, measuring a push that faint, without letting the plates crash together or catch on a speck of dust, lay far beyond the tools of Casimir's time. Then, in 1997, a physicist named Steve Lamoureux finally pinned it down. Using instruments sensitive enough to feel a force smaller than the weight of a single red blood cell, he measured the plates drawing together. The number matched Casimir's 50-year-old prediction almost exactly. The vacuum had pushed, and a human being had felt it. This was a turning point. Until then, the seething vacuum could be waved away as a quirk of the mathematics, a bookkeeping device nobody had to take too seriously. The Casimir experiment slammed that door shut. The energy of empty space is real. It presses on metal. It moves objects you could hold in your hand. And the plates were only the beginning. If the restless vacuum truly surrounds everything, then it should be pressing on far more than metal. It should be pressing on the particles inside every atom, nudging them, disturbing them in ways we could measure. The only question was whether anyone could build an instrument precise enough to catch it. Someone did, and when they aimed that instrument at a single electron, the vacuum left behind a fingerprint so exact that it became the most precisely tested prediction in the entire history of physics. An electron behaves like a tiny magnet, and the strength of that magnet can be both predicted by theory and measured by experiment. When physicists compared the two, they uncovered the clearest fingerprint the vacuum has ever left. Every electron spins in a way that makes it act like a minuscule bar magnet. Basic theory predicts a certain strength for that magnet, a clean and simple value. But when experimenters measured the real thing, the electron came out very slightly stronger than the simple prediction. The gap was tiny, out in the far decimal places. Something was adding a whisper of extra magnetism. That something is the vacuum. As the electron sits there, the fizzing sea of virtual particles around it never leaves it alone. Ghostly pairs flicker into being right beside it, tug on it, and vanish. The electron is forever wrapped in a shifting cloud of these borrowed particles, and that cloud alters its magnetism by a hair. To predict the electron's true strength, you have to add up the effect of the whole churning crowd around it. So physicists did. They calculated how much the seething vacuum should shift the electron's magnetism, working through layer after layer of virtual particles, each one a smaller correction than the last. Then they compared that prediction against the measured value. The two numbers agree to more than 10 decimal places. To put that level of agreement into human terms, it is like measuring the distance from New York to Los Angeles, about 2,500 miles, and having your calculation match the true distance to within the width of a single human hair. No other prediction in all of science has ever been confirmed so precisely, and that staggering match is only possible if the vacuum is real. The extra magnetism comes entirely from those flickering virtual particles. Strip them out of the calculation, and the answer collapses. Put them back in, and it becomes the most accurate agreement between theory and reality humans have ever achieved. The vacuum is written into the electron itself, to more than 10 decimal places. There is more. That same restless vacuum reaches into atoms and shifts the energy of their electrons by a tiny, measurable amount, a nudge first spotted in the light glowing off hydrogen. Everywhere physicists looked closely enough, the fingerprints of empty space were waiting, faint but unmistakable, exactly where the theory said they would be. So the picture is now locked in place, and it is rock solid. Empty space quivers with energy that can never be removed. It fizzes with particles borrowed and repaid in an endless churn. It pushes on metal plates. It reshapes the magnetism of the electron to a precision beyond anything else in science. On this, the evidence is overwhelming and past serious doubt, which is exactly what makes the next step so disturbing. If the vacuum is this real, if its energy shows up in every careful measurement we make, then that energy must have a grand total. There must be some actual amount of it packed into every empty region of space. And when physicists set out to calculate that total, using the very same trusted theory that had just nailed the electron to 10 decimal places, the machine that had never failed them handed back an answer that made no sense at all. To add up the energy of the vacuum, you start from a rule you already know. Every point in space, every field, carries that permanent quiver, and every quiver holds a small amount of energy. The total energy of empty space is simply the sum of all those quivers. So you begin adding them up. The trouble is the wavelengths. The vacuum's quivering fields ripple at every possible size, from long, lazy waves down to shorter and shorter ones with no obvious bottom. Each wavelength carries its own dose of energy. And here is the cruel part. The shorter the wave, the more energy it holds. The tiniest ripples, the ones vibrating fastest, pack in the most. So, as you add up the contributions, you march towards smaller and smaller waves, and each new step throws more energy onto the pile than the step before. The sum refuses to settle down. It climbs, and the closer you look, the more furiously it climbs. because there is always a smaller wavelength waiting with even more energy to add. Left alone, the total races off toward infinity. That cannot be the real answer, so physicists draw a line. They pick a smallest possible wavelength and refuse to count anything below it, a size where they suspect their current understanding of space and time simply stops working. That boundary has a name. It is called the Planck scale, and it is unimaginably small. An atom, compared to it, is larger than the entire solar system compared to that atom. Stopping the sum at the Planck scale seems reasonable. Below that size, nobody knows how space itself behaves, so nobody counts it. With that line drawn, the total finally becomes a finite number instead of an infinite one. The calculation can be finished. You can write down an actual figure for how much energy fills every cubic inch of empty space. This is the same standard, trusted approach that produced the electron prediction we just celebrated, the one that matched reality to more than 10 decimal places. The mathematics behind it is the crown jewel of modern physics. Generations of the sharpest minds in the field have checked and rechecked it. When it speaks, physicists listen, because it has almost never been wrong, so they ran the sum all the way down to the Planck scale, and they got their finite number for the energy density of the vacuum, a real, concrete value for how much energy hides inside nothing. Then they turned around and looked at the universe itself to see how much vacuum energy was actually out there, because the energy of empty space is more than a number on a chalkboard. It has a real effect on the cosmos. It pushes on space. It shapes how the universe grows and stretches across billions of years. That means the universe carries its own answer, written all the way across the sky, that anyone can go out and measure. They had two numbers now, one from the trusted theory, one from the real universe. All that remained was to lay them side by side and check that they matched, the way the electron had matched so perfectly before. The two numbers did not match. They missed each other by an amount so vast that when physicists first saw the gap, many of them assumed they had simply made a mistake. When physicists finally laid the two numbers side by side, they were staring at the largest failure in the history of science. The trusted theory predicted a certain amount of energy packed into empty space. The universe, measured directly across the sky, revealed a completely different amount, and the gap between them was overwhelming. The predicted value overshot the real one by a factor with roughly 120 zeros after it. In the whole history of human thought, no calculation has ever missed reality by so much. Physicists have a blunt name for this. Some call it the vacuum catastrophe. Others simply call it the worst theoretical prediction in the history of physics. And that harsh verdict comes from the very people who built the theory. The same framework that had just described the electron more precisely than anything humans have ever measured. The exact machine that produced the most accurate prediction in all of science also produced the most catastrophically wrong one. Both answers poured out of the same equations. That is what makes it a true crisis rather than an ordinary mistake. If the theory was sloppy, you could throw it away and start fresh. But this theory works. It works better than anything else we have ever built. It predicts the behavior of particles, light, and atoms with breathtaking accuracy, again and again, in experiment after experiment. Then you ask it the simple question of how much energy fills empty space, and it fails by a margin almost too large to write down. Something is deeply broken, and nobody knows what. Either our best theory of the very small has missed something enormous about the vacuum, or our understanding of gravity and space has missed something equally enormous, or both at once. The failure sits precisely on the border between the physics of the tiny and the physics of the cosmos, the two great pillars holding up modern science. And it whispers that those pillars do not fit together the way we always believed. For more than half a century, this has been one of the deepest unsolved problems in all of physics. Some of the most brilliant minds who ever lived have thrown themselves against it. They have proposed hidden cancellations, secret symmetries, undiscovered particles, extra dimensions, folded out of sight. Every attempt has fallen short. The catastrophe still stands, unexplained, an open wound at the very center of our picture of reality. And physicists cannot simply shrug and move on. The energy of the vacuum is no private matter for the equations. It has weight. It bends space. It shapes how the entire universe expands and evolves across billions of years. A number that wrong about the vacuum is a number that wrong about the fate of everything, which is why the mismatch is far more than an academic embarrassment. If the prediction were correct, the consequences for the universe would be beyond catastrophic. That much energy crammed into every cubic inch of space would not sit there quietly. It would do something violent to the cosmos, something that should have made your very existence impossible. To feel why, you first have to feel the size of the number itself. 120 zeros is a figure so far outside human experience that ordinary words fall away from it. So, before we ask what all that energy would do, we have to try, carefully, to grasp just how monstrously large it truly is. A 1 followed by 120 zeros is a number the human mind was never built to hold. We can say it out loud in a second. Feeling it is another thing entirely. So let us walk toward it slowly, one comparison at a time, until the sheer size of it settles into place. Start with something huge. Count every grain of sand on every beach and every desert on Earth. Scientists have actually estimated this. The answer is roughly 7 followed by 17 zeros. An enormous number, far beyond anything you could ever count in a lifetime. Yet against 120 zeros, all the sand on Earth is not even a beginning. It barely clears the starting line. Push further. Count every star in the observable universe, across every galaxy we can see. That gives you around a 1 with 23 zeros behind it. Still nowhere close. Now count every atom in every one of those stars, in every planet, in every cloud of gas, across the entire cosmos. All the atoms in the observable universe come to about 1 with 80 zeros. 80 zeros. And we need 120. Sit with that for a moment. If you took every single atom in the entire visible universe, every atom in every star and world, and drifting speck of dust across billions of galaxies, you would still be short by a factor of a 1 with 40 more zeros stacked on top. The gap between the vacuum's prediction and its reality is larger than the universe measured atom by atom many times over. There is a way to feel it that hits even harder. Imagine you are an engineer measuring a distance, and you make an error of 120 orders of magnitude. Picture setting out to measure the width of a single atom and being wrong by that margin. Your answer would not be off by a room, or a city, or a planet. It would overshoot the width of the entire observable universe and keep going and going, dwarfing the whole cosmos many times over, all while you thought you were measuring something smaller than a speck of dust. That is the scale of the mistake sitting at the heart of our best theory. That is how badly the calculation misses, and the reason it deserves the name catastrophe becomes clear once you picture what all that energy would actually mean if it were real. Because energy is not just a number in an account. Energy has an effect. It reaches out and grips space itself. The more energy you cram into a region, the more powerfully it pulls on the fabric of the universe and warps the way space behaves. The vacuum's predicted energy is so unthinkably vast that its grip on space would be violent beyond imagining. So the question stops being about mathematics and becomes about survival. If empty space truly held the energy our theory predicts, the universe could not possibly look the way it does. It could not hold still long enough for stars to form, for planets to gather, for a single living thing to draw breath. That much energy would seize the cosmos in the first instant and never let go. To understand why your existence would be impossible, we have to watch what that monstrous energy would have done to the universe the moment it was born. Give the vacuum the energy our theory predicts, and the universe destroys itself before it can even begin. Here is why. Energy grips space. This is one of the deepest lessons of Einstein's work. Energy and matter do more than sit inside the universe. They bend it, stretch it, and steer the way it grows. Pack energy into a region, and that energy tells space how to move. The more energy, the more violent the command. Now feed in the vacuum's predicted energy, that value with 120 extra zeros, filling every cubic inch of space at once. The command it would give the universe is overwhelming. It would seize the fabric of space everywhere, all at the same instant, and wrench it apart with unimaginable force. The universe would not expand gently, it would tear. Every region of space would fly away from every other region so ferociously that nothing could ever hold together. Atoms could never form, because the space between their pieces would rip open faster than any force could pull them close. Stars could never gather, galaxies could never assemble. The cosmos would be blown into a thin, cold, formless mist in a fraction of a second, and it would stay that way forever, far too violent and empty for anything to ever grow inside it. There would be no chemistry, no planets, no warmth, no time for anything interesting to happen at all. A universe carrying the vacuum energy our theory predicts is a universe where structure is impossible, where nothing can ever clump, connect, or come alive. It is a dead sheet of scattered energy, ripped so thin that even the idea of a place inside it loses meaning. And yet, look around. You are here. Atoms held together long enough to build stars. Stars burned long enough to forge the carbon and oxygen and iron inside your body. Galaxies gathered. Planets cooled. Life crawled up out of the chemistry on at least one small world. The universe is not a ripped and lifeless mist. It is structured, patient, and old. 13.8 billion years and still building. So the universe we actually live in flatly contradicts the universe our best theory demands. The prediction says everything should have been torn to nothing in the first instant. Reality says everything held together well enough to make you. Both cannot be right. And reality, obviously, wins. You are the proof that the calculation is broken. This is why the vacuum catastrophe keeps physicists awake. It is a place where our most trusted theory does more than get a number wrong. It predicts a universe with no stars, no worlds, and no observers. And then a universe full of exactly those things wakes up and reads the prediction. The theory has been contradicted by the most stubborn evidence there is: your own existence. Something must be holding the vacuum energy down, cancelling almost all of it, taming a value that should have been apocalyptic into something the universe can survive. Whatever that something is, it works with almost perfect precision. And here is the twist that turns the whole mystery on its head. The cancellation is not quite perfect. A tiny sliver of vacuum energy does survive. And when astronomers went looking for it in the depths of space, they found it, hiding in the way the universe is expanding right now. In 1998, 2 teams of astronomers set out to measure how fast the expansion of the universe was slowing down. They found the opposite. It was speeding up. To understand why that shook the field, remember what everyone expected. The universe has been expanding since the Big Bang, with all the galaxies flying apart. Gravity pulls matter together, so gravity should be gently putting on the brakes, slowing that expansion over billions of years. The 2 teams wanted to measure how hard the brakes were being applied. They studied exploding stars in distant galaxies, using them as markers to track how the expansion had changed across cosmic history. The exploding stars told a story nobody wanted to hear. Instead of slowing down, the expansion of the universe had been picking up speed. The galaxies are not merely drifting apart, they are being pushed apart, faster and faster, by something that behaves like a pressure built into space itself. Something is fighting gravity across the entire cosmos and winning. Astronomers gave that something a name. They call it dark energy, and it makes up a staggering share of the universe, roughly 68% of everything there is. More than 2/3 of the cosmos is this mysterious push, this energy woven into empty space, driving everything apart. And here is where the threads tie together. a pressure built into empty space, present everywhere, driving the universe to expand, is exactly what leftover vacuum energy would do. The seething vacuum we have been chasing all along is the leading suspect behind dark energy, the energy of nothing, the churn of virtual particles, the quiver that can never be stilled, appears to be gently pushing the entire universe apart right now. So the vacuum energy is not zero after all. The near-perfect cancellation that saved the universe from being ripped apart left a tiny remainder behind, and that remainder is real. We can measure it. It is written across the sky in the accelerating flight of the galaxies. Empty space carries a faint, genuine energy, and over billions of years that faint energy is reshaping the destiny of the cosmos. This discovery was so important that it earned the Nobel Prize. It confirmed that the universe holds a small, steady vacuum energy, exactly the kind of thing our theory had been fumbling to describe. In one sense, it was a triumph. The vacuum energy was found, weighed, and pinned down. In another sense, it made the crisis far worse, because now physicists had the real number in hand, measured straight from the heavens, and they could set it beside the number the theory predicted. The theory said the vacuum should hold a monstrous energy, that value with 120 zeros. The universe answered with a whisper, a value fantastically, delicately small. The catastrophe was no longer only that the two numbers disagreed, it was that reality had chosen such a bizarrely tiny, finely balanced value, one that sits almost, but not exactly, at zero. And a number that sits almost exactly at zero, but not quite, is one of the most unsettling things a physicist can find. It hints that the universe has been tuned with a precision so extreme it borders on the absurd, as if someone had balanced a pencil on its point and walked away. Suppose you are told that two enormous numbers, each vast beyond imagining, cancel each other out almost perfectly, leaving behind a remainder that is fantastically close to zero, but not quite there. Your first instinct would be to ask who arranged that, and how. That instinct is exactly what haunts physicists about the vacuum. The measured vacuum energy is not zero. If it were zero, physicists could hope that some clean rule forces it to vanish completely, a rule that switches the whole thing off in one stroke. A value of exactly nothing can feel natural. There are ways to make things cancel to nothing. That would be a puzzle, but a solvable-looking one. Instead, the universe handed us a value that is almost zero, tiny beyond belief, delicately small, yet stubbornly present. And that is far harder to explain. It means the giant vacuum energy predicted by theory has been cancelled away to an astonishing number of decimal places, with one faint sliver left over at the very end. The cancellation is nearly total, but it stops just short of perfection, and it stops at exactly the right place to give the universe we see. Think about what that requires. You have a colossal positive contribution to the vacuum energy and a colossal negative one, both staggeringly large. They must cancel each other, digit for digit, through dozens upon dozens of decimal places, matching almost flawlessly. Then, at the very bottom, one final tiny mismatch survives, and that mismatch is the dark energy pushing our galaxies apart. If the cancellation had been even slightly less precise, the leftover energy would have been far too large, and the universe would have torn itself apart or crushed itself shut long ago. Physicists call this a fine-tuning problem, and it is one of the deepest discomforts in all of science. Picture balancing a needle perfectly upright on its tip and having it stay there for billions of years. Picture setting dozens of dials, each one to a value it has no reason to choose, and finding every single one landed on precisely the number needed for stars, planets, and life. That is the situation the vacuum energy presents. Nothing in our theory explains why the cancellation should stop where it does. It simply does, with a precision that feels almost designed. And physicists do not like the word designed. They want a reason, they want a mechanism, a rule, a hidden piece of machinery that forces the vacuum energy to be small without anyone having to tune it by hand. A universe that only works because dozens of numbers happen to line up perfectly feels less like an explanation and more like a lucky accident begging to be understood. So the problem sharpened into a single burning question. What natural process could take that monstrous predicted energy and shave it down, almost but not quite to nothing, landing on the exact tiny value we observe? What could do the cancelling, cleanly and automatically, without a cosmic hand on the dial? For decades, one idea seemed to hold the most promise. It was elegant, powerful, and beloved by theorists around the world. It proposed a hidden partner for every particle in nature, partners whose contributions to the vacuum would neatly cancel the ones we already knew. It was the great hope for solving the catastrophe. And when physicists finally went looking for those hidden partners, the universe gave them an answer that broke a generation of dreams. The great hope was called supersymmetry, and for decades it looked like the answer that could tame the vacuum. The idea was beautiful in its simplicity. For every kind of particle we already know, supersymmetry proposed a hidden partner, a heavier twin waiting to be discovered. Every ordinary particle would have its shadow counterpart, matched to it by a deep symmetry woven into the laws of nature. Here is why that mattered for the vacuum. When physicists worked out how different particles contribute to the energy of empty space, they noticed something elegant. The known particles push the vacuum energy in one direction. Their proposed partners would push it in exactly the opposite direction by exactly the same amount. Pair each particle with its twin, and their contributions would cancel, one cancelling the other, cleanly and automatically. If that were true, the monstrous vacuum energy would tame itself. There would be no need to balance dozens of dials by hand. The symmetry would do the work for free, forcing the giant contributions to erase one another and leaving a small, sensible remainder behind. The fine-tuning nightmare would dissolve into an elegant piece of natural bookkeeping. That is why theorists loved it. It was clean, it was powerful, it felt right. For years, supersymmetry was the odds-on favorite to solve the deepest problems in physics. And not only the vacuum, it also promised to explain other stubborn puzzles, and it offered a natural candidate for the invisible dark matter that holds galaxies together. Whole careers were built on it. Thousands of papers explored it. Many of the sharpest physicists alive were certain that when the next great machine switched on, it would find these hidden partners at last. That machine was the Large Hadron Collider, the most powerful particle accelerator ever built, buried in a ring beneath the border of France and Switzerland. It smashes particles together at nearly the speed of light, recreating conditions not seen since the earliest moments of the universe. If the partner particles existed anywhere near the energies physicists hoped, this was the machine that would conjure them into view. The collider ran. It reached higher and higher energies. Physicists watched the wreckage of countless collisions, searching for the telltale signs of the hidden twins. They found nothing. No partner particles appeared, not at the energies supersymmetry needed, not in the clean and simple form that would have solved the vacuum problem. Search after search came back empty. The elegant twins that were supposed to cancel the vacuum energy stubbornly refused to show themselves. This does not prove supersymmetry is entirely wrong. The partners could still exist, hiding at energies far beyond our reach. But the simple, beautiful version, the one that would have neatly cancelled the vacuum energy and rescued us from fine-tuning, has been badly wounded. If those partners exist at all, they sit so high that their cancellation no longer works cleanly, and the fine-tuning problem comes creeping back, reduced but unresolved. So the great hope faltered, and the catastrophe still stood. The vacuum energy remained monstrously predicted, whisperingly small in reality, and stubbornly unexplained. Physicists were left staring at an empty collider and an open wound. With the elegant fixes failing one after another, some physicists turned to an idea so radical, so uncomfortable, that many of their colleagues consider it barely science at all. If the vacuum energy cannot be explained by any rule, some physicists say, then perhaps it needs no rule at all. Perhaps it is simply the value it has because, in any universe where it were different, no one would be alive to ask the question. This is the anthropic idea, and it turns the whole problem inside out. Instead of asking why the vacuum energy is so finely tuned, it asks who could possibly be here to notice if it were not, and the answer is no one. We already saw that a large vacuum energy rips the universe apart before stars can form. So any universe with a large vacuum energy is a dead universe, empty of observers, empty of anyone to wonder about it. Now take the next step, the one that makes this idea so strange. Imagine our universe is only one of a vast, perhaps limitless collection of universes, each born with its own value of vacuum energy. Most of them get a monstrous value and tear themselves to shreds, lifeless and silent. A rare few, by pure chance, land on a tiny value, small enough that stars, planets, and living things can form. Those few become homes for observers. In this picture, the fine-tuning stops being a miracle and becomes a filter. Of course, we find ourselves in a universe with a friendly vacuum energy. We could not exist anywhere else. Asking why our vacuum energy is so perfectly small is like a fish asking why its particular patch of ocean happens to be full of water. The fish could not have arisen in a dry patch. We could not have arisen in a torn one. Physicists call the imagined collection of universes the multiverse, and they call this style of reasoning the anthropic principle. Together, they offer a way to explain the fine-tuning without any hidden machinery. No symmetry, no cancelling partners, no dial balancing. Just an enormous lottery of universes, and the unremarkable fact that we live in a winning ticket because losing tickets have no one to read them. For some physicists, this is a genuine breakthrough, the only idea that survives when all the elegant fixes have failed. It fits naturally with certain deep theories that already suggest a huge landscape of possible universes, each with different laws. To them, the multiverse is not a wild guess. It is where the mathematics was pointing all along. For many others, it feels like a surrender. A real explanation, they argue, should predict something you can go out and test. The multiverse, by its nature, hides its other universes forever beyond our sight. We can never visit them, never measure them, never confirm they are there. An idea that can explain any value at all, simply by saying some universe somewhere has it, starts to feel less like science and more like a story we tell to make the discomfort go away. That deep divide runs right through the field to this day. Some of the brightest minds in physics find the anthropic answer compelling. Others find it a dead end dressed as a solution. The argument is far from settled, and it may never be, but whatever you think of the multiverse, it leaves the core mystery untouched. The vacuum energy is real, and it is only one face of a stranger truth, because empty space carries more than a hidden energy. It carries a hidden field, switched on everywhere, and that field is the reason you have any weight at all. There is a field filling all of space that has been switched on since the beginning of the universe, and without it, you would have no mass at all. You would fly apart into weightless pieces, racing away at the speed of light. It is called the Higgs field, and it lives in the vacuum. Most fields in nature rest at zero when nothing disturbs them. Turn off every source, clear away every particle, and they relax to nothing, quiet and empty. The Higgs field breaks that habit. Even in the emptiest vacuum you can imagine, with every particle stripped away, the Higgs field holds a steady, non-zero value. It sits switched on everywhere, all the time, a permanent feature of empty space itself. Picture the universe soaked in this field, the way a sponge is soaked through with water, evenly, everywhere, by default. There is no place you can go to escape it. The room around you, the space between the stars, the void between galaxies, all of it is filled with the same steady presence, and certain particles, As they move through this ever-present field, feel it. The field resists their motion, drags on them, clings to them. That resistance is what we experience as mass. The more strongly a particle grips the Higgs field, the harder the field pulls back, and the heavier that particle becomes. A particle that clings tightly is heavy. A particle that barely notices the field is light. And a particle that ignores the field entirely, like the particle of light itself, carries no mass at all and sails through untouched, forever at the speed of light. So your weight, the heft of every atom in your body, traces back to how the particles inside you interact with an invisible field woven into the vacuum. Empty space is not a passive backdrop. It reaches into matter and hands out mass. Strip the Higgs field out of the vacuum, set its value to 0, and the particles that make you would lose their mass and scatter into a weightless blur. You exist as a solid, weighty thing because the vacuum decided, long ago, to switch this field on and leave it on. In 2012, physicists at the Large Hadron Collider confirmed the Higgs field was real by finding its telltale particle, a discovery hailed as one of the greatest in the history of science. The field we had suspected for decades turned out to be there, exactly as predicted, quietly giving the universe its substance. But confirming the field was only the start of the trouble, because a field switched on in the vacuum raises a question that turns out to be far more dangerous than it first appears. Why does the Higgs field rest at the particular value it does, and not some other? Every field seeks out its resting value, the way a ball rolls down into the bottom of a valley and settles there. The Higgs field has rolled into its valley, its steady switched-on level, and settled. That value shapes the mass of every particle and the structure of everything built from them. And here is the question that has begun to keep physicists up at night. Is the valley our Higgs field rests in truly the lowest point there is, or is it merely a shallow dip with a far deeper valley waiting somewhere beyond, hidden out of sight? Imagine a ball resting in a small dip partway up the side of a mountain. It looks perfectly settled. It sits still. Nothing seems to be pulling it anywhere. But the dip it rests in is not the bottom of the mountain. Far below, past a ridge it cannot see over, lies a deeper valley. The ball only needs a strong enough nudge to escape its little dip, and it would go tumbling down, down, to a resting place, far lower than the one it knows. This is the question hanging over the Higgs field and over the entire universe. The steady value the Higgs field rests in, the switched-on level that gives every particle its mass, sits in a valley. The whole future of the cosmos depends on one thing. Is that valley the true bottom of everything, or only a ledge above a deeper drop? Physicists describe the possible resting places of the Higgs field using a shape they call the Higgs potential. Picture it as a landscape of hills and valleys, where every point tells you how much energy the field would have if it settled there. The field, like the ball, wants to roll to the lowest point it can reach. Where the lowest point actually lies decides the fate of the vacuum. If our valley is the true bottom, then all is well. The Higgs field is resting in the lowest place there is. It will stay there forever. The vacuum is stable, and the laws of physics we know are locked in for all time. Nothing could ever knock the field loose, because there is nowhere lower for it to go. But if our valley is only a ledge, a shallow dip perched above a deeper valley hidden beyond a ridge, then the picture turns dark. It would mean the vacuum we live in is not the lowest, truest state of the universe. It would be a false resting place, a temporary perch. And somewhere out there, past a barrier, a deeper valley would be waiting, a truer vacuum with less energy, calling the field to fall. Physicists call these two possibilities a stable vacuum and a metastable vacuum. A stable vacuum rests at the true bottom, safe forever. A metastable vacuum sits on a ledge, seemingly calm, but with a deeper drop lurking beyond. From the inside, the two look almost identical. The field sits still. Everything appears settled. You cannot tell by glancing around whether the ground beneath you is bedrock or a thin shelf above an abyss. So, how could anyone possibly know which one we live in? We cannot see over the ridge. We cannot peer into the shape of the Higgs potential far from where the field rests today. The deeper valley, if it exists, lies at field strengths beyond anything we can reach directly. The answer is astonishing. The shape of that distant landscape, the very part we cannot see, is decided by the masses of particles we have already measured. The Higgs potential is pulled and bent by the particles that interact with the field, and their tug shapes whether a deeper valley opens far away or whether the ground holds firm. Two particles matter most in this hidden tug-of-war. One tries to open the abyss. The other fights to keep the ground solid. And when physicists measured their masses and worked out who wins, the contest came out so close it made their blood run cold. The shape of the hidden Higgs landscape, the part that decides whether a deeper valley waits beyond the ridge, is not fixed once and settled. It is pulled in opposite directions by two of the heaviest players in all of physics, locked in a quiet tug-of-war. On one side stands the top quark, the heaviest particle we have ever discovered. As it constantly interacts with the Higgs field through the churning vacuum, it drags on the distant shape of the landscape, pulling it downward. At field strengths far beyond where we rest today, the top quark's pull tends to bend the potential lower and lower, threatening to open a deeper valley out there and turn our home into a mere ledge above it. On the other side stands the Higgs particle itself through its own mass. It pulls the opposite way, working to lift the distant landscape, to keep the potential rising and our valley the true bottom. One particle tries to carve out the abyss, the other tries to seal it shut. Whether a deeper valley opens far away comes down to which of these two pulls is stronger. And this is the part that unsettles physicists. When you measure the two masses and put them into the equations, the contest comes out almost exactly even. Not a clear win for stability, not a clear win for the abyss. The two pulls very nearly cancel, leaving the fate of the vacuum balanced on the finest of edges. The heavy top quark drags the landscape down. The Higgs pushes it up, and the result of that struggle, based on the best numbers we have measured so far, lands right at the boundary between a vacuum that is safe forever and a vacuum that is merely pretending to be. Picture two people of nearly equal strength pulling on opposite ends of a rope, straining with everything they have, and the knot in the middle barely moving. That is the state of our vacuum. The masses we have measured, the top quark on one side and the Higgs on the other, place us right at the knife edge, in a delicately poised situation that could tip either way. This balance is so precise it feels almost deliberate, and physicists do not know what to make of it. There is no obvious reason the two masses should be so exquisitely matched. They could have come out wildly different, tilting the universe firmly toward safety or firmly toward collapse. Instead, they landed within a hair of the dividing line, as if the universe were balanced on the point of a needle. The current best measurements lean, ever so slightly, toward the unsettling side. They hint that our valley may indeed be a ledge, that a deeper vacuum may wait beyond the ridge, and that the ground beneath the laws of physics may not be bedrock after all. The uncertainty is real, and small shifts in the measured masses could nudge the answer one way or the other. But the leaning is there, and it points toward a vacuum that only looks stable. If that leaning is correct, then we are living inside a false vacuum, a perch, a shelf above a drop, and a false vacuum, no matter how calm it seems, carries a possibility that is difficult to sit with once you understand it fully. To live in a false vacuum is to live on a ledge that looks, feels, and behaves exactly like solid ground, right up until the instant it does not. Everything around you would seem perfectly stable. The Higgs field sits in its valley. Particles carry their familiar masses. Atoms hold together. Stars burn. Chemistry works. Life thrives. From the inside, a false vacuum is indistinguishable from a true one. There is no warning sign, no tremor, no slow warming or cooling to tip you off. The universe simply carries on, calm and ordinary, for billions of years. And yet, if our valley is only a ledge, then the universe has somewhere lower to fall. The true vacuum, the deeper valley beyond the ridge, holds less energy than the one we live in. And nature always prefers less energy. A ball on a ledge above a deeper valley is not in its final resting place. Given the chance, it will fall. The only thing keeping it up is the ridge, the barrier standing between the shelf and the drop. In the everyday world, a ball stuck in a dip on a hillside stays there unless something shoves it over the ridge. But the quantum world plays by stranger rules. Down at the smallest scales, a system trapped behind a barrier does not always need a shove to escape. It can pass straight through the barrier, as if the wall of the ridge were not fully there. This ghostly passage is one of the most well-established facts in all of physics, seen countless times in experiments. Particles slip through barriers they could never climb over. The Higgs field can do the same. Even without any nudge, even sitting perfectly calm in its valley, the field has a tiny chance, at any moment, of tunneling straight through the ridge and appearing in the deeper valley beyond. It does not need heat. It does not need a trigger. It only needs time and the rules of quantum chance. Sooner or later, somewhere, the field can simply leak through to the lower state. And when it does not happen everywhere at once. It begins at a single point, in one tiny patch of space, where the Higgs field slips through the barrier and drops into the true vacuum. In that one spot, the field abandons the value it has held since the birth of the universe and settles into the deeper valley, the truer resting place. A microscopic seed of the true vacuum blinks into existence inside our own. That seed is the beginning of the end, because the true vacuum, holding less energy, is more stable than the false one around it. The patch does not sit quietly. It grows. The boundary between the old vacuum and the new one, a thin shell of pure energy, races outward, swallowing the false vacuum and converting everything it touches into the true state. A single bubble is born, filled with a truer, deeper vacuum, and it begins to expand into the world we know. Inside that bubble, the Higgs field rests at a new value. The masses of particles change. The delicate balances that allow atoms and chemistry and life fall apart. Everything the bubble reaches is remade under different laws. And the way that bubble grows, the speed and violence of its expansion, is where the true horror of vacuum decay finally reveals itself. A single bubble of true vacuum has appeared, smaller than an atom, and now it begins to grow. The bubble grows because it is more stable than the world around it. Inside sits the deeper vacuum, holding less energy. Outside sits our familiar false vacuum, holding more. Between them stretches a thin shell, the wall of the bubble, where one vacuum gives way to the other, and that wall does not sit still. The energy released as the false vacuum converts into the true one pours straight into the wall, driving it outward, feeding it, pushing it to grow. Here is the terrifying part. As the wall races outward, all that released energy keeps pumping into it, and the wall keeps accelerating. There is nothing to slow it down. The vacuum offers no friction, no resistance, no drag of any kind. Every scrap of energy freed as the bubble expands goes into making it expand faster. Within moments, the wall is screaming outward at very nearly the speed of light, the ultimate speed limit of the universe, the fastest anything can ever move. Think of a spark landing on a vast field of dry grass, except this fire needs no oxygen, feels no wind, and burns across a field with no far edge. Once it catches, it spreads outward in every direction, and each patch it ignites feeds the flames pushing into the next. But a grass fire crawls. This wall flies, almost as fast as light itself, and it never burns out, never runs low on fuel, never finds a fire break it cannot cross. It simply expands, faster and faster, swallowing the false vacuum whole, and the bubble grows in every direction at once. From that first microscopic seed, it swells into a sphere of true vacuum, its wall rushing outward on all sides, converting everything it reaches. A patch the size of an atom becomes the size of a room, then a world, then a solar system, then a galaxy, in less time than the words take to say. The sphere of the true vacuum expands without limit, eating the old universe and replacing it with the new. Nothing can outrun it, because nothing can move faster than light. Nothing can hide from it, because it comes from every direction the wall expands into. And nothing can stop it, because the wall grows stronger the more it consumes. Once a single bubble forms and takes hold, the outcome is sealed. The old vacuum is finished. It is only a matter of how long the wall takes to arrive. This is what makes vacuum decay so unlike any other disaster the universe can produce. A supernova fades. A black hole stays put. Even the collision of galaxies unfolds over hundreds of millions of years, slow enough to watch. The bubble of true vacuum is different. It is fast beyond fast, unstoppable and total. It does not damage the universe. It replaces it, converting the old cosmos into a new one, governed by different laws, one expanding sphere at a time. And the closer you look at that wall, the worse it gets. Because the boundary of the bubble is more than a fast-moving edge. It is the exact place where the laws of physics you have known your entire life stop being the laws that apply. Cross that threshold, and everything that holds you together comes undone. Step across the wall of the bubble, and you enter a region where the rules that built you no longer hold. Inside the bubble, the Higgs field rests at its new, deeper value. And remember what the Higgs field does. It hands out mass. It decides how heavy every particle is. Change its value, and you change the mass of everything. Inside the true vacuum, particles would carry entirely different masses than they do in our world. Some might become far heavier. Some might lose their mass completely. The delicate arithmetic that lets particles bind into atoms would be rewritten from the ground up. And that arithmetic is not forgiving. The atoms in your body, in this planet, in every star, exist only because the particles inside them have exactly the masses they do. The electron, the quarks, the forces that hold them together, all of it is balanced on the values set by our vacuum. Shift those values, and the balance shatters. Atoms could no longer hold together. The chemistry that builds every molecule, every cell, every living thing would simply cease to be possible. So when the wall of the bubble sweeps over you, it does not burn you or crush you in any ordinary sense. It dissolves the very possibility of you. The particles that make your body would be forced into a new set of masses and rules, and the structures they form, atoms, molecules, cells, would come apart because those structures cannot exist under the new laws. Everything the bubble touches is unmade at the deepest level and remade into whatever the true vacuum allows, which may be nothing recognizable at all. Physicists who study this have described it in stark terms, calling vacuum decay the ultimate catastrophe, an event that destroys not just life, but the conditions that make life possible anywhere it reaches. A supernova wipes out a star system. A gamma-ray burst could sterilize a region of a galaxy. Vacuum decay is in a different category altogether. It does not end life. It ends the chemistry that life is built from. Everywhere the bubble expands, forever. To feel the difference, imagine the difference between a fire that burns down a library and a change to the alphabet itself that makes every book unreadable everywhere, all at once. The fire is a local tragedy. The second is a rewriting of the rules that no amount of rebuilding could undo. Vacuum decay is the second kind. It does not destroy the contents of the universe. It rewrites the language the universe is written in, and it would spread across everything. The bubble does not stop at a planet or a star or a galaxy. Its wall keeps racing outward at nearly the speed of light, converting galaxy after galaxy, reaching across the cosmos over billions of years, turning the entire observable universe into the new vacuum given enough time. Everything we can see, every star and world and structure that took nearly 14 billion years to build, would be swept into the deeper valley and remade. There is one small mercy hidden in this horror, though the word mercy sits strangely here. The wall travels at almost the speed of light, and that single fact means that when the end comes for any of us, we would have no idea it was coming at all. Picture the bubble wall racing toward Earth from somewhere out in the galaxy, moving at very nearly the speed of light. Now ask a simple question. What could warn you it was on the way? The answer is nothing. And the reason cuts to something deep about how the universe works. Light is the fastest messenger there is. No signal, no warning, no ripple of any kind can travel faster than light. The bubble wall itself moves at almost exactly the speed of light, so the wall and any light announcing it arrive at practically the same instant. The flash that might warn you and the wall that would consume you reach you together. There would be no glow on the horizon, no shadow growing across the sky, no tremor in the ground, no scientist's alarm ringing out in time to matter. The bubble could already be halfway across the galaxy, closing in at the speed of light, and every telescope on Earth would show a calm, ordinary sky right up until the final instant. The warning cannot outrun the threat, because nothing can. And when the wall did arrive, it would pass through you faster than your nerves could fire, faster than a single thought could form. The particles of your body would be remade under the new laws before any signal could travel from one cell to the next. There would be no pain, because pain takes time, and there would be no time. There would be no fear, because fear needs a warning, and there would be no warning. One instant you would exist. The next, in less time than it takes a single atom to register anything at all, you and the world around you would simply be gone, converted into the true vacuum without a trace. The whole planet would go the same way, all at once, or as near to all at once as makes no difference. The wall would cross the entire Earth in a tiny fraction of a second, sweeping from one side to the other faster than a heartbeat. There would be no survivors, no ruins, no aftermath to study, because there would be no one left under the old laws to study anything. The Earth would not be destroyed so much as erased and overwritten. Strangely, this makes vacuum decay one of the gentlest disasters imaginable, precisely because it is one of the most total. There is no suffering, no struggle, no slow decline. There is no dread, because no one ever knows. The universe would simply switch from one set of laws to another, and everything built on the old laws would quietly cease, without ever knowing it had happened. Consider how different this is from every disaster we usually fear. An asteroid can be spotted years in advance. A dying sun swells over millions of years. Even the slow cooling of the universe unfolds over spans so vast they lose meaning. Vacuum decay hides all of that behind the speed of light. It is the one catastrophe that gives no notice whatsoever, that could be underway right now, somewhere out there, and we would have no way to know until the final, silent instant. That thought is enough to keep anyone awake. So it is worth asking the obvious next question. How likely is any of this, really? Because there is a piece of reassuring mathematics that physicists reach for, and for most purposes, it lets them sleep at night. Before the fear takes hold completely, there is a number that physicists cling to, and it is a comforting one. Even if our vacuum truly is a false one, sitting on a ledge above a deeper valley, the chance of it decaying at any given moment is extraordinarily small. The barrier between our vacuum and the deeper one, the ridge the Higgs field would have to tunnel through, is high and wide. Tunneling through it is possible, but wildly unlikely on any short span of time. The field would have to slip through by pure quantum chance in one tiny patch of space, and the odds of that happening anywhere nearby, anytime soon, are almost unimaginably low. How low? When physicists work out the expected lifetime of our vacuum, assuming nothing disturbs it, they get a span of time so long it makes the current age of the universe look like the blink of an eye. Our universe has existed for nearly 14 billion years. The expected time before our vacuum might decay on its own, according to the best estimates, is vastly, staggeringly longer than that. Longer than the universe has existed. Longer than it will exist in any form we would recognize. So long that for every practical purpose, the moment may as well never come. Put in human terms, worrying about spontaneous vacuum decay tomorrow is like worrying that all the air in your room will randomly drift into one corner and leave you gasping. The laws of physics permit it. The odds are so absurdly small that it will never happen in the entire lifetime of the cosmos. The vacuum, even a false one, is expected to hold for spans of time that dwarf every clock nature has. This is why physicists can study vacuum decay calmly, write papers about it, and still go home and sleep. On the timescales that matter to human beings, to civilizations, even to the lifetime of the sun and the earth, the risk is effectively zero. The sun will swell and die in a few billion years. The earth will be long gone, and through all of it, the vacuum is expected to sit quietly on its ledge, undisturbed, exactly as it has since the beginning. So in one sense, the honest answer is reassuring. If our vacuum is metastable, it is the slowest motion catastrophe imaginable, one that will almost certainly never touch us or anyone who comes after us for a length of time beyond all meaning. The quiet panic among physicists is not that the sky will fall tomorrow. It is a deeper unease about what the knife-edge balance is trying to tell us about the universe. But notice the quiet assumption hiding inside that comforting number. The enormous lifetime, the reassuring span, longer than the age of the cosmos. All of it assumes one thing. It assumes the vacuum is left alone. It assumes nothing reaches in and gives the Higgs field a push. Nothing lowers the barrier. Nothing helps the field over the ridge. The estimate is for a vacuum decaying purely by chance, undisturbed, on its own. And the universe is not always a gentle, undisturbed place. There are events out there of such violence and such extremity that they could, in principle, do what random chance almost never would. They could nudge the field, they could thin the barrier, they could light the fuse early, and that is where the reassurance begins to fray. The comforting lifetime of the vacuum rests on a single condition. Nothing disturbs it. Break that condition, and the numbers change. The slow, reassuring estimate describes a vacuum decaying on its own by pure quantum chance, in perfect calm. But the universe is full of violence. Stars explode, black holes collide, particles smash together at energies that dwarf anything in daily life. And in the most extreme of these events, conditions can arise that make tunneling through the barrier easier, that give the Higgs field the nudge it would never get from chance alone. Here is the worry in plain terms. The barrier between our vacuum and the deeper one is not equally hard to cross under all conditions. Pour enough energy into a small enough region, and you effectively lower the ridge, or give the field a running start toward it. In the right kind of extreme environment, the odds of the Higgs field slipping through stop being astronomically small and start creeping toward possible. The fuse that random chance would take longer than the universe to light might, under the right violent conditions, catch far sooner. This is what turns vacuum decay from a distant abstraction into a real question physicists take seriously. If some event, somewhere, could trigger the decay early, then the reassuring timescale no longer fully protects us. The question becomes not how long the vacuum lasts on its own, but whether anything in the universe, natural or otherwise, is capable of setting it off ahead of schedule. And the moment you ask that question, an uncomfortable one follows close behind. Humans build machines that create the most extreme energies ever produced on Earth. In the great particle colliders, physicists smash particles together at nearly the speed of light, reaching energies that recreate conditions not seen since the earliest instance of the universe. If extreme energy can lower the barrier, could one of our own machines, in principle, be the thing that lights the fuse? The thought has genuinely troubled people. When the most powerful collider ever built was switched on, a handful of voices worried aloud that smashing particles at such energies might do something catastrophic, might poke a hole in the vacuum itself and start a bubble that would consume the world. The concern reached far beyond physics departments. Some feared that in the hunt to understand the universe, we might accidentally end it. It is a chilling idea. We spend this entire story afraid of distant, cosmic triggers, and then realize the most extreme energies in our corner of the universe are the ones we make ourselves, deliberately, in a tunnel beneath the ground. The machines built to reveal the deepest secrets of the vacuum are also, in principle, the machines that reach the conditions where the vacuum is most vulnerable. So the question is deadly serious, and it deserves a serious answer. Could a particle collider on Earth trigger the decay of the vacuum and destroy everything? Physicists have thought about this long and hard, and the reason they can switch those machines on with confidence comes from an unlikely source. Streaking through space, striking our atmosphere every single day, and carrying far more power than anything we could ever build. The reason physicists can run the most powerful colliders on Earth without fear comes from the sky, and it has been raining down on us for billions of years. They are called cosmic rays, particles flung across space by exploding stars, black holes, and other violent engines of the universe. Traveling at nearly the speed of light, they strike the Earth's atmosphere constantly, day and night, in staggering numbers. And here is the crucial fact. The most energetic cosmic rays carry far more energy than any particle our machines have ever produced. Nature routinely accelerates particles to energies that make our greatest colliders look gentle. Now follow the logic that lets physicists sleep. These ultra-high energy cosmic rays have been slamming into things for the entire history of the universe. They crash into our atmosphere, they crash into the moon, the sun, and every planet. They crash into one another out in deep space. Across nearly 14 billion years, all over the cosmos, particles have been colliding at energies far beyond anything we can create, countless times, in numbers beyond counting. If a collision at those energies could trigger the decay of the vacuum, it would already have happened, somewhere, sometime, in all those billions of years, and all those countless violent impacts. A cosmic ray collision would have lit the fuse. A bubble of true vacuum would have formed and swept outward at the speed of light, and the universe as we know it would already be gone. But it is not gone. We are here. The stars still shine. The old laws still hold. The universe, in other words, has already run the experiment for us, on a scale and at energies we could never match, again and again, for billions of years. And it has survived every single time. That is powerful evidence that collisions at these energies simply cannot trigger vacuum decay. Our own machines reach energies well below what cosmic rays achieve routinely. If nature's far more violent collisions have never set off the vacuum, ours, being weaker, cannot either. So the fear of a collider ending the world, though it sounds terrifying, does not survive contact with this simple argument. Every time we smash particles together, we are doing something the universe has done to itself trillions upon trillions of times already, at higher energies, without harm. The machines are safe, not because we are clever enough to be sure, but because the cosmos has been running the same test since the beginning and passing it every time. This is one of the more elegant pieces of reasoning in all of physics. We cannot directly prove our vacuum will never decay, but we can point to the sky and say, whatever we do down here, nature has already done worse, and here we still are. The survival of the universe across billions of years of cosmic violence is itself the safety certificate for our experiments. And yet, the reassurance is not total. Cosmic rays rule out one kind of trigger, the sudden violent collision. But there are other, stranger ways the vacuum might be nudged, ways that do not involve smashing particles at all. In recent years, physicists have turned their attention to a far more exotic suspect, an object so extreme that it might not need a collision to crack the vacuum open. It might do it simply by existing, and then by dying. There is an object in the universe so extreme that it might not need to smash anything to threaten the vacuum. It might do it simply by being there, and then by fading away. That object is a black hole. Black holes are the most extreme concentrations of gravity in the cosmos, regions where matter has collapsed so completely that not even light can escape. And near a black hole, space and the fields woven into it are bent and stretched to a degree found nowhere else. Physicists have started to ask a disturbing question. Could the extreme conditions around a black hole make it easier for the Higgs field to tunnel through the barrier and start a bubble of true vacuum? The idea works something like this. A black hole warps the vacuum around it so severely that the delicate balance keeping the Higgs field on its ledge could be disturbed. In the intense gravity near the horizon, the barrier that normally holds the field in place may become easier to cross. The black hole, in effect, could act as a seed, a weak point where the vacuum is more likely to give way and a bubble more likely to be born. It gets stranger when the black hole starts to die. Black holes are not truly eternal. Over immense spans of time, they slowly leak energy and shrink, a process that speeds up as they get smaller. A shrinking black hole grows hotter and more violent as it approaches its final moments, concentrating extreme conditions into a smaller and smaller region. And in that fierce final stage, some calculations suggest the conditions could become just right to nudge the Higgs field over the edge and nucleate a bubble of true vacuum. Recent research has explored exactly this. Physicists have found that a single, ordinary black hole is not enough to threaten us, but a large population of tiny black holes, especially the kind that might have formed in the extreme conditions of the early universe, could be a real danger. If enough of these small, rapidly evaporating black holes existed, the chance that one of them would seed vacuum decay would climb from negligible toward genuinely worrying. Here is the twist that turns this into evidence, rather than only fear. We are still here. The vacuum has not decayed. So if tiny black holes really could seed vacuum decay so readily, then there cannot have been very many of them in the history of the universe. Our survival becomes a measuring tool. The fact that no bubble has swallowed us tells physicists something real about how many small black holes the early universe could have made. The absence of catastrophe is itself a clue. So black holes join cosmic rays in a strange double role. They are a possible trigger for the ultimate disaster, and at the same time, our continued existence in a universe full of black holes becomes evidence about how stable the vacuum really is. Every day the sky stays calm is another data point, another small confirmation that whatever weak points exist, they have not yet been enough. All of this raises a question that reaches back to the very beginning. The early universe was the most violent, extreme environment that has ever existed, far hotter and wilder than anything today. If extreme conditions can trigger vacuum decay, then the young universe should have been the deadliest moment of all. So how did the vacuum ever survive its own birth? If extreme conditions can threaten the vacuum, then the most dangerous moment in all of history was the very beginning, when the universe was hotter, denser, and more violent than it has ever been since. And that raises a genuine puzzle. How did our vacuum survive being born? Go back to the earliest instance after the Big Bang. The universe was a furnace beyond imagining, packed with energy at scales that dwarf anything in the cosmos today. In that inferno, the Higgs field was buffeted by enormous fluctuations, violent shudders in every field, energies vastly higher than anything a collider or a cosmic ray could ever reach. If any conditions could kick the Higgs field over its barrier and into the deeper valley, surely these were them. There was also a period very early on when the universe is thought to have expanded at a staggering rate, ballooning in size almost unimaginably fast. During that stretching, light fields, like the Higgs, would have been shaken by large fluctuations, jolted this way and that. Each jolt was a chance for the field to slip over the ridge into the true vacuum. With so much violence and so many chances, the young universe looks like the perfect place to trigger the catastrophe we have been dreading. And yet it did not happen. The Higgs field, somehow, stayed on its ledge through the most extreme conditions the universe has ever known. It weathered the furnace, endured the violent expansion, and settled into the calm valley we live in today. The vacuum survived its own birth, against what looks like steep odds. That survival is a real clue, and physicists take it seriously. The puzzle is sharp. If our vacuum is metastable, sitting on a ledge as the measurements hint, then the wild early universe should have knocked the Higgs field loose. The fact that it did not suggests one of a few possibilities, and each one is interesting. Perhaps the early universe did not expand quite as violently as the simplest pictures suggest, keeping the fluctuations gentle enough to spare the field. Perhaps there is new physics we have not yet discovered, some undiscovered particle or force that stabilized the Higgs field in those early moments and kept it safe. Or perhaps our measurements of the particle masses are slightly off, and our vacuum is more stable than it currently appears. In every case, the survival of the vacuum through the Big Bang is telling us something we do not yet fully understand. It is a constraint written into our own existence. We are here, which means the young universe did not destroy its own vacuum, which means either the early universe or the laws of physics are arranged in a way that protected it, working out which is one of the live puzzles at the frontier of the field. So our existence keeps handing us clues from the deepest past, clues about inflation, about hidden particles, about the true stability of the vacuum, all encoded in the simple fact that a bubble never formed in the fire of creation. The universe left us a mystery in the ashes of its own birth. For a long time, all of this lived only in equations and arguments, impossible to test. You cannot rewind the Big Bang. You cannot wait out a decay time longer than the age of the cosmos. But physicists have found a clever way around that wall, and they are now doing something that once seemed unthinkable. They are building tiny, controlled versions of a false vacuum in the laboratory and watching it decay. For decades, vacuum decay was a story physicists could only tell with mathematics, impossible to witness. You cannot trigger a real vacuum decay to study it, for reasons that should be obvious, and you cannot wait out a decay time longer than the age of the universe. So physicists found a clever way to sneak up on the problem. They built a stand-in. The idea is to create a different physical system that follows the same underlying mathematics as a decaying vacuum, then watch that system in the lab. If the equations match, the small, safe system can reveal how the terrifying cosmic one would behave. It is a way of studying the end of the universe without risking anything at all. To do it, physicists reach for one of the coldest, strangest states of matter ever made. They take a cloud of atoms and chill it to a temperature almost unimaginably close to absolute zero, colder than the deepest depths of space. At that extreme cold, the atoms lose their individual identities and merge into a single, coordinated quantum state, a kind of matter that behaves as one unified whole. In this exotic state, physicists can carefully arrange the atoms so that the system sits in a false state, poised to decay into a truer one, exactly mirroring the mathematics of a false vacuum. Then they watch, and in recent years, in laboratories doing exactly this, they have seen it. In the frozen atomic cloud, tiny bubbles of the true state have appeared, nucleating out of the false one, just as the theory of vacuum decay predicts. The bubbles form, they grow, they spread through the cloud. For the first time, physicists have watched the birth of a true vacuum bubble, not in the cosmos, but in a controlled system on a laboratory bench, small enough to hold and safe enough to repeat. This is a genuine breakthrough. For the first time, the abstract mathematics of vacuum decay, worked out on paper for half a century, has been tested against real physical behavior. The lab bubbles are not the end of the universe. They are a safe, shrunken echo of it. But they follow the same rules, and by studying how they form and grow, physicists can check their theories, refine their calculations, and understand the mechanics of a process that would otherwise remain forever out of reach. The experiments are still young, and the frozen atomic clouds cannot capture every detail of a real cosmic vacuum. Gravity, the true shape of the Higgs landscape, and the full violence of the early universe all lie beyond what a small cloud of atoms can reproduce. The lab bubbles test the machinery of decay, not the exact odds of it happening to our universe. Physicists are careful to say so. They have built a model of the process, not a crystal ball for our fate. Still, the achievement is remarkable. We have taken one of the most apocalyptic ideas in all of physics and coaxed a tiny, harmless version of it into existence on a tabletop, where we can study it in daylight, the end of the universe, in miniature, playing out in a cloud of atoms colder than space. And watching those bubbles form raises a question that circles all the way back to the beginning of everything. If a vacuum can decay from a false state into a truer one, then who is to say it has only happened once? Who is to say our laws of physics are the original ones, and not the aftermath of a decay that already occurred long before the universe we know began? Watching a false vacuum decay into a truer one in the lab plants a strange and vertiginous thought. What if it has happened before? What if the laws of physics we live under are not the first ones, but the survivors of a decay that already took place? Follow the logic. A false vacuum can decay into a deeper one, and inside the new bubble, the laws of physics are different. The masses of particles change. The balances that govern matter shift. So the laws inside a true vacuum bubble are not the laws that came before it. They are new, born from the collapse of an older vacuum. Now turn that around and point it at our own universe. What if our vacuum, the one we call home, is itself the inside of a bubble, the aftermath of some earlier vacuum that decayed long ago? In this picture, there was once a different vacuum, with different laws, governing an earlier phase of reality. At some point, a bubble of a deeper vacuum formed within it and swept outward, remaking everything it touched. And we live inside the region it remade. The laws we study, the particles we measure, the delicate balances we marvel at, would all be the settled wreckage of that ancient transition, the new rules that took hold after the old ones were swept away. This idea reframes our entire situation. The fine balances that let atoms and life exist, the finely tuned values we struggle to explain, might not be fundamental at all. They might be the particular outcome of whichever vacuum our universe happened to fall into, one option among many that a decay could have produced. The laws would feel eternal and absolute to us, simply because we have never known anything else. The way a fish knows only the water it was born in, and it opens a dizzying possibility about the future. If our vacuum decayed from an earlier one, then it may not be the last word either. Our vacuum could be one more ledge in a long staircase, with deeper valleys still waiting below. A future decay could remake the laws again, birthing yet another set of rules in yet another bubble. The universe, in this view, is not a fixed stage with permanent laws. It is a landscape of possible vacuums, and reality tumbles down through them, one transition at a time, whenever chance or violence tips it over an edge. Physicists are careful with this idea, and rightly so. It is speculation built on solid mathematics, a possibility the equations permit rather than a fact anyone has proven. We have no direct evidence that our vacuum descended from an earlier one, and we may never find any, since a bubble erases the world that came before it. The idea sits at the edge of what physics can responsibly say, fascinating and unprovable in the same breath. But it captures something important about where all of this leads. The deeper physicists dig into the vacuum, the less it looks like a fixed, empty backdrop, and the more it looks like something with a history, a structure, and perhaps a future of its own. The vacuum is turning out to be the most important object in physics, and the least understood. And that lack of understanding is not a small gap at the edges. It points to a crack running through the very foundation of physics, a place where our two greatest theories meet and flatly refuse to agree. The vacuum sits at the exact spot where the two greatest theories in physics meet, and it is there, in the emptiness, that they come to blows. Modern physics rests on two towering achievements. One describes the very small, the world of particles and fields, the quantum realm where the vacuum churns with virtual pairs and zero-point energy. The other describes the very large, the world of gravity, space, and time, where energy bends the fabric of the cosmos and steers the motion of galaxies. Each theory is spectacularly successful in its own domain. Each has been tested and confirmed to breathtaking precision, and the vacuum is where they are forced to speak to each other. Here is why that meeting turns violent. The theory of the small says the vacuum is full of energy, that seething quantum energy we have chased through this entire story. The theory of the large says that any energy, including the energy of the vacuum, must bend space and shape how the universe expands. Put the two together, and the theory of the small hands the theory of the large, a monstrous vacuum energy, and the theory of the large replies that such energy would have torn the universe apart. The two cannot both be right as they stand. Their meeting produces the vacuum catastrophe, the worst prediction in the history of physics. This is the deepest reason the vacuum unsettles physicists. The catastrophe is not a small error inside one theory. It is a sign that our two greatest theories, quantum physics and gravity, do not fit together. They work beautifully apart. They contradict each other in the vacuum, and the vacuum is the one place in the universe where you cannot keep them apart, because empty space is governed by both at once. The energy of nothing is quantum. Its effect on space is gravitational. There is no avoiding the collision. For a century, physicists have searched for a deeper theory that would unite the two, a single framework that describes the quantum and the gravitational in one language. Such a theory, often called a theory of quantum gravity, would presumably explain the vacuum properly at last, taming its energy and resolving the catastrophe. But despite enormous effort by the finest minds in the field, no complete and confirmed theory of quantum gravity yet exists. The unification remains one of the greatest unsolved problems in all of science. So the vacuum is more than a curiosity or a lurking danger. It is a signpost. It marks the exact location where our understanding breaks down, where the two pillars of physics grind against each other and fail to mesh. Whatever the true, deeper theory of reality turns out to be, it will have to make sense of the vacuum, because the vacuum is where the current theories most spectacularly disagree. That is why physicists keep returning to empty space, again and again, despite how strange and frustrating it is. They are convinced that the answer to the deepest question in physics, how the quantum and the gravitational fit together, is hiding in the nature of the vacuum. Solve the vacuum, and you may solve the crack running through the foundation of everything. And when they follow that crack down to its very bottom, to the smallest scale physics can even describe, they find the vacuum doing something wilder than anything we have seen so far. At the tiniest scale of all, empty space may stop being smooth and start to boil so violently that space and time themselves come apart. Zoom in on empty space, closer and closer, past atoms, past particles, down to the smallest scale physics can even describe, and something extraordinary may happen. Space itself stops being smooth. That smallest scale has a name. It is the Planck scale, the same tiny boundary where the vacuum energy calculation ran into trouble. It is unimaginably small, so small that an atom compared to it is vaster than the entire solar system compared to that atom. At sizes above the Planck scale, space looks smooth and continuous, like the calm surface of a lake seen from far above. But physicists suspect that if you could look at the Planck scale itself, that smoothness would dissolve into something violent. At that scale, the restless energy of the vacuum becomes so intense that it may warp space and time themselves. Remember that energy bends space. Down at the Planck scale, the quantum fluctuations of the vacuum carry so much energy in so small a region that they could bend space wildly, chaotically, from one tiny patch to the next. Instead of a smooth backdrop, space would seethe and churn, twisting and tearing and healing over and over, faster than any clock could follow. Physicists have a name for this idea. They call it space-time foam. Picture the ocean again, but now imagine diving all the way down to the finest scale of its surface. What looked like smooth water from above reveals itself, up close, as a chaos of froth and spray, bubbles forming and bursting, the surface constantly tearing and reforming. Space-time foam is that image, applied to the fabric of reality itself. At the Planck scale, space and time may not be a smooth stage at all. but a boiling, frothing chaos, where the very notions of distance and duration lose their meaning. If this picture is right, then the vacuum is far stranger than even the churning sea of virtual particles suggested. At the deepest level, empty space would not simply contain restless energy. It would be made of restless energy so intense that the structure of space and time comes undone. The smooth, reliable stage on which all of physics plays out would be an illusion, a calm average over a violence we cannot yet see, a froth of tearing and mending geometry at the bottom of everything. Nobody has observed space-time foam directly. The Planck scale lies fantastically far beyond the reach of any experiment we can currently build, and it may stay beyond reach for a very long time. The idea comes from pushing our theories to their limits and asking what the vacuum should do when quantum energy and gravity meet at the smallest scale. It is a prediction of the frontier, not yet a confirmed fact, but it follows naturally from taking the seething vacuum seriously all the way down, and it deepens the mystery rather than resolving it. The smoother and calmer empty space looks to us, the more violent it may be underneath, all the way down to a scale where space and time themselves may dissolve into foam. The vacuum we began with, a quiet nothing in a sealed box, has become the most turbulent, structured, and enigmatic thing in all of physics. All of which forces us, finally, to ask the largest question of all. If the vacuum holds this much hidden power and hidden danger, then what does it mean for the ultimate fate of everything? How does the universe actually end? Everything we have uncovered about the vacuum points toward a single, sobering question. How does the universe end? And the vacuum offers two very different answers, two rival endings, and it is not certain which one reaches us first. The first ending is slow, quiet, and almost gentle. It comes from the vacuum energy we measured across the sky, the dark energy pushing the galaxies apart. That push is not fading. If anything, it drives the expansion of the universe faster and faster over time. Follow it far enough into the future, and the consequences are stark. Galaxies are carried so far apart that they vanish from one another's skies. Stars burn out and are not replaced. Matter itself slowly decays and disperses. The universe grows colder, darker, and emptier, drifting toward a final state of near-perfect nothingness, spread thin and frozen, where nothing ever happens again. Physicists call this ending the heat death, and it unfolds over spans of time so vast they defy comprehension, far longer than the current age of the universe, stretching into a future so distant the numbers lose all meaning. It is the universe running down like a clock that will never be wound again, every fire burning out, every structure crumbling, until only cold, dark, silent emptiness remains, and it is driven, at bottom, by the vacuum energy woven into space. The second ending is fast, violent, and total. It is the one we have been circling this entire story. If our vacuum is truly a false one, a ledge above a deeper valley, then one day, somewhere, a bubble of true vacuum may form and sweep outward at the speed of light, remaking the laws of physics and erasing everything the old universe built. This ending gives no warning and leaves no trace. It does not run the universe down slowly. It overwrites it in an instant, converting the cosmos we know into something governed by different rules entirely. So the universe stands poised between two fates, and both trace back to the vacuum. One is the long, cold fade of the heat death, driven by the dark energy of empty space. The other is the sudden, silent overwrite of vacuum decay, driven by the possibility that our vacuum is not the true bottom. The same mysterious nothing that fills every corner of the cosmos holds the keys to both endings. Which one comes first? On our best current understanding, the slow fade is the more likely fate on the timescales physicists can estimate. Vacuum decay, if it comes at all, is expected to take even longer than the long, cold winding down. So vast is the time before a bubble would spontaneously form. The universe would most likely grow cold and empty long before any bubble had a realistic chance to swallow it. But the honest answer is that we do not know for certain. The knife-edge balance of our vacuum, the loopholes that could trigger early decay, the gaps in our understanding, all leave the question genuinely open. Both endings share one feature. In each, the vacuum has the final word. The nothing that seems so empty, so passive, so beneath our notice, is the very thing that decides how everything ends. And that is precisely why the people who understand the vacuum best are the ones who find it hardest to look away. Here is what unsettles physicists most, and it is not the fear of a bubble arriving tomorrow. It is something quieter and, in its way, harder to shake. The vacuum has become the place where our understanding of the universe visibly breaks. Our best theory predicts a vacuum energy so wrong it should have destroyed the cosmos, and offers no accepted explanation for why it did not. The measured energy sits at a value so finely balanced it looks almost impossible. Our vacuum may be a false one, poised on a knife edge between safety and collapse, and we cannot say for certain which side it will fall on. And beneath it all, our two greatest theories meet in the vacuum and flatly contradict each other. Every one of these problems is real, serious, and unsolved. That is the source of the quiet unease. Not panic in the sense of alarm about immediate danger. On the timescales that matter to human life, the vacuum is expected to hold, and the great catastrophes lie unimaginably far in the future, if they come at all. The unease runs deeper than that. It is the recognition that the most ordinary thing in the universe, the empty space that fills every gap and surrounds every object, is something we fundamentally do not understand. The nothing that seems simplest turns out to be the hardest thing in all of science. Physicists live with this in a particular way. They can calculate the behavior of particles to more than 10 decimal places, the most precise predictions humanity has ever made. And in the same breath, they must admit they cannot explain why empty space has the energy it does, or whether the ground beneath the laws of physics is solid or a thin shelf above a drop. The same field that has mastered the universe to astonishing precision is humbled completely by nothing at all. There is a strange humility in that, and also a strange thrill, because a problem this deep, this stubborn, this central, is exactly the kind of problem that has, throughout history, cracked open into revolution. Every time physics has run into a wall this fundamental, the answer, when it finally came, remade our entire picture of reality. The unsolved vacuum is not only a source of unease, it is a signpost pointing toward the next great leap in human understanding, whenever it comes. So the honest state of the field is a mixture of calm and awe. Calm, because the sky is not about to fall, and the reassuring timescales hold for every purpose that touches human life. Awe, because the vacuum has revealed itself to be the most important and least understood object in the universe, the place where the deepest secrets are hiding, the crack through which the next theory of reality may one day shine. The people who understand the vacuum best are not lying awake in terror, they are lying awake in wonder, turning over a mystery they know is enormous, sensing that the answer, when it arrives, will change everything we think we know about the fabric of existence. And that leaves one final thing to understand, the most important of all, not what the vacuum threatens or what it hides, but what it means, right now, for you, sitting inside a universe built on a foundation of restless, mysterious nothing. Before we close, there is a hopeful truth hidden inside all this uncertainty, and it is worth holding on to. Every great crack in physics has been a doorway, and the vacuum may be the widest doorway of all. Look back at the history of the field. Each time physicists ran into something they could not explain, something that broke their best theories, the eventual answer did more than patch the hole. It opened a new world. The strange behavior of light and heat led to quantum mechanics and the entire electronic age. The puzzles of space and time led to relativity and our modern understanding of the cosmos. The problems that seemed most maddening, most impossible, turned out to be the seeds of the deepest revolutions. A wall in physics has a habit of becoming a window. The vacuum may be exactly that kind of wall. The catastrophe of its energy, the knife edge of its stability, the contradiction between our two great theories, all of it signals that something profound is missing from our picture of reality. And missing pieces this large do not stay missing forever. Somewhere in the tension of the vacuum, physicists believe, lies a clue to the theory that will finally unite the quantum and the gravitational, the framework that has eluded the greatest minds for 100 years. There are real reasons for optimism. We can now build tiny false vacuums in the laboratory and watch them decay, turning an untestable idea into an experiment. We are measuring the masses that decide the vacuum's fate with ever greater precision, sharpening the picture year by year. We are mapping the expansion of the universe, chasing the dark energy that fills empty space with a new generation of telescopes. Each of these efforts chips away at the mystery, and any one of them could deliver the surprise that cracks the whole problem open. None of this guarantees an answer soon. The deepest problems are the slowest to yield, and the vacuum may keep its secrets for a long time yet, but the direction is unmistakable. For the first time in history, the vacuum is becoming something we can probe, test, and measure, rather than only wonder about. The nothing that seemed forever beyond reach is being coaxed, slowly, into the light of experiment. So the quiet unease among physicists carries a bright thread running through it. The vacuum is a crisis, yes, a place where our understanding fails. But it is a crisis of the most promising kind, the kind that has always, eventually, given way to a greater understanding of the universe than anyone imagined possible. The very thing that unsettles physicists most is also the thing that excites them most, because they know what a mystery this deep has always led to. The universe has hidden its greatest secret in the most unlikely place, in the emptiness that surrounds you, the nothing you have never once thought about. And when we finally understand that nothing, we may understand everything else along with it, which brings us back to you and to the strangest realization of all. The empty space you have ignored your entire life is not empty, not passive, and not simple. It is the most powerful and mysterious thing in the universe, and you are living inside it, made from it, held together by it at every single moment. Look at the space around you, the ordinary air, the gaps between objects, the emptiness you have never once thought to question. You have spent your whole life believing that empty space is the one thing in the universe that is truly nothing, and you have been wrong the entire time. The nothing around you seethes with energy that can never be switched off. It fizzes with particles borrowed and repaid 1 trillion times over in every instant. It presses on metal plates and reshapes the electron to more than 10 decimal places. It carries an energy so vast our best theory should have torn the universe apart, and yet leaves behind a whisper so finely balanced it borders on the miraculous. That same nothing gives you your weight, holds your atoms together, and decides how the entire universe will one day end. The emptiest thing you can imagine turns out to be the fullest, the most powerful, the most alive. And here is the truth that ties it all back to you. You are not a solid object moving through empty space. You are a pattern held together by the vacuum itself. The mass of every atom in your body comes from a field switched on in the emptiness. The forces binding your particles reach through the churning vacuum. The very stability of the matter you are made of depends on the vacuum resting quietly on its ledge, as it has since the birth of the cosmos. You are, in the most literal sense, a structure built on nothing, and that nothing is the most extraordinary thing in existence. This changes how you might see the world, if you let it. The empty sky overhead is not a void. It is an ocean of restless energy, stretching to the edge of the observable universe. The space between you and the person across the room is not truly empty. It is full of flickering particles, humming fields, and the quiet presence of the vacuum that fills all things. You have been swimming in this ocean your entire life, made of it, sustained by it, never once noticing it was there. Physicists do not fully understand this ocean, and they are honest about that. They cannot yet explain its energy, cannot yet say for certain whether its foundation is solid, cannot yet unite the theories that meet inside it and disagree. The vacuum remains the deepest unsolved mystery in all of science, hiding in the most ordinary place there is. But that mystery is not a reason for fear. On the time scales of your life, and your children's lives, and the life of the sun itself, the vacuum holds steady, patient, and quiet, exactly as it always has. What it offers instead is wonder. The universe kept its greatest secret in the last place anyone thought to look, in the emptiness we dismissed without a second glance. And once you know it is there, you can never quite see empty space the same way again. The nothing is not nothing. It is the stage, the substance, and the story of everything, including you. So the next time you find yourself staring into empty space, remember what is really there. Not silence, not stillness, not a void. An ocean of energy, seething with hidden power, holding the universe together and holding the deepest questions in all of science. The most important thing in existence has been in front of you the whole time, disguised as nothing at all.